Hello everybody. Goedendag Amsterdam. Let's see, ik ben Clemens Vastos. Mijn groep in Microsoft is the messaging team. I can do this a little bit. I'm dangerous enough in my Dutch that if you talk to me in Dutch or amongst each others about me, I will understand. I live so close to the Dutch border that I actually drove here in a little less than 2 hours. So I live in Viersen, which is 15 kilometers from Venlo. And so I'm kind of, and I go to Limburg for lunch, which I just already hear you don't consider part of your country sometimes. All right, so I'm the architect for, one of the architects for messaging really, at Microsoft, and I live in Germany. I work out of my house mostly, and then I shuttle over to US every once in a while. And what I want to talk about is messaging and some scenarios where that messaging is being used, and also trying to answer the question why we have so many messaging services, because we just presented a new one. If you followed the news at the serverless conference and at Ignite, we have a new thing that's called Event Grid. I'll also talk about that a bit. But that raises the question, now you have this relay, you have Service Bus, you have Event Grid, you have event hubs, you have IoT hub. There's so many things that move stuff around. Why is that so? So I'm going to try to shed some light on that. Messaging used to be a very dangerous thing to be in. Things have improved a little bit, so we no longer have to risk death daily. As in the Pony Express, as it says here, the wages are also a little bit better than $25 per week. And you don't need to be orphans. But messaging has always been something, way before computers, has been something that has been driving our society, and also has been driving our businesses, and also wars, tallying up, batch processing, holorith machine. Here you have a postal service, a telegraph service, and there's a motor courier who then continues sending that data, so there's routing happening, right? Here you have the pneumatic tube station of Sears and Roebuck. So that's kind of their mail order business, and how they kind of did all the dispatching between the incoming orders and dispatching that out to the various departments, which then would go fulfill the order. So this is the broker, effectively, the broker room of Sears, back in the early 1900s. Obviously, mail, not email, but postal mail, airmail, has been the biggest driver of aviation. In the early days, in the 1910s, 1920s, nobody was stupid enough to get on one of those planes, except if you're very adventurous. But it made postal mail very fast. So the earliest use of airplanes for communication was through airmail, or for any commercial use actually, was for mail. As time progressed with mail, we had numerous additional capabilities that were added to mail. So first of all, you obviously, on an envelope, you make annotations. You first say where the mail goes to, but then you have quality of service additions that you put on top of that. So for instance, here we have a Einschreiben, certified mail. What that says is that this is now a trackable envelope. You don't throw it in, but you actually can go to the post office and can go and track where that is. And it's also asking for a return receipt, which makes this a reliable delivery mechanism, because you actually get a response back when that has been delivered. These are extra quality of service capabilities which have been layered on top of that messaging stack. That is the postal mail service. And all those capabilities are being echoed in the electronic messaging systems, in the application-to-application messaging systems that we use today. But very few of these are new. The first time someone came up with the electronic version of that was IBM, and IBM as part of IBM OS 360, specifically the telecommunications subsystem, and 360 was built in the 1960s. The copyright here is 1965. That's the first time that a queue showed up as infrastructure in a system like this, and IBM OS 360 was one of the operating system pushes that happened during the Apollo age, where the Apollo program, Apollo program was put together from hundreds of thousands of people with hundreds of thousands of parts. And just to manage that supply chain, they needed to have something that was sophisticated computer systems that didn't exist at the time. So IBM, being part of this, came up with that. So that's the first time queues appeared. Queues are meanwhile, or queues or messaging systems are meanwhile kind of powering the backbone of everything that we do. In financial services, there's various forms. All of your bank transfers, everything you do as an electronic wire transfer, really every time you book something into your account, you do any kind of transfer, any rebooking, that lands invariably in a queue. All of the financial data that is used to drive markets with very low latency is happening through different kinds of queues, through different queuing infrastructures. But it's all done through some sort of messaging system. There's high speed, low latency, volatile messaging systems, and then there's super highly reliable messaging systems, depending on what your use case is. Financial services is driven effectively by messaging infrastructure. Industrial automation becomes more and more driven by messaging infrastructure, because there is now a trend that has been started or has started around the world, but there's a formal initiative by the German government that you may have heard of, Industry 4.0, that resonates in many different places in the world. The German government started that initiative because the Germans have something to lose in industrial manufacturing, leadership, if someone overtakes them on the digital side. And one of the great themes of this Industry 4.0 story is predictive maintenance. Is being able to improve the quality of your industrial systems, like this line here, which is a bottling plant. Improve the quality of these by having insights into how things behave and continuously monitoring them to be able to make predictions on when things break. And that's something that, as someone who has their head in IT, for us, things don't necessarily break. Like, computers work, they have a lifetime of like 2 years, 3 years, and yeah, they break, but that's mostly just an accident. Something just gets wedged, and otherwise they just work. And then because time kind of progresses and things get faster, you throw them out anyways. But if you think about industrial manufacturing, things break on a schedule because there's real wear and tear. There's physical exposure to the elements, and you have tools, and those tools wear. So you have cases where you have tools that are being used to drill holes into metal, and those tools will be used 20 times. And then they're going to be tossed out. Maintaining identical quality of that hole that's being drilled, because sometimes you really need to have super high precision, and actually timeliness of that process means that you probably need to go and treat that differently. Many machines, anything that rotates, relies on ball bearings, fans, motors, everything. By now you can predict to the hour when a ball bearing will break by just having the vibrations monitored of that thing. You have to go and collect a lot of data, you need to flow a lot of data, you need to go and learn from that data, and you need to have analytics somewhere. That is now causing these closed systems in manufacturing to open up to sophisticated analytics systems, which are built in IT technology, to communicate. That is happening through messaging, through eventing. We'll hear more about that. The energy grid in Europe, for instance, is completely integrated. There is a organization in Brussels that is the organization ENTSO-E, ENTSO-E, and ENTSO-E is the organization, a federation of all the electricity transport providers in Europe. The electricity market is split up into effectively 3 pillars: producers, distributors, you're paying your bill to a distributor, and transport operators. And the transport operators are the ones who are operating the high towers. And these are 3 completely different sets. What they do is they make sure that if there's no wind on the North Sea, that there's enough power from somewhere else to supplant that missing energy that doesn't come down from Denmark or that doesn't come down from Holland. Because it's a wholly, completely integrated grid across the entire EU. That whole coordination, the market making, because obviously if power flows from country to country and from company to company, there's money involved. All of that is driven by messaging systems. And there's this whole giant space about intelligent mobility, connected car, this sharing of resources or sharing of cars, Uber and Lyft in the United States being some of the key pioneers in that space, however ethical. And then there's a lot of new models for how mobility is made to work. We will need to have a lot of information exchange and information flow to make autonomous driving work, because every single one of us has an absolutely fantastic driving computer in their head with an unbeatable perception system. Computers don't have that. Computers can't do the classification work that we can do easily, and you can say AI 100,000 times, they need help. So what the help that you need is pre-classified information, updated high-definition maps. And updating those high-definition maps and even getting those high-definition maps requires a lot of data flow. That data flow also is messaging. And then, of course, all games, television, consumer web, adware, and ad tech, so all the advertising is all done through some form of, or driven by some form of messaging, right? Interactive game shows work today with messaging in the form of the carrier's SMS systems, which is fantastic. And it's the thing that keeps the SMS system alive. Why? You're being charged 50 cents for every SMS that you send as you vote for something, and those SMSs alone are enough to pay for that TV show. So all of those casting shows and music entertainment and Everybody Dances with the Stars and all those things, they're basically being funded by you voting for things, which is awesome. And that's something that's being done through messaging and microbilling, really, in combination. Games are now depending a lot on telemetry. One problem that the Halo team had, here you have, it's not the Master Chief, but it's one of those guys. One of the problems that the Halo team had before Halo 5 was not really knowing what was going on in their multiplayer maps. Multiplayer maps, so multiplayer games in these on the console games, or really anywhere, are really peer-to-peer coordinated. So there's a primary and there's a secondary, but it's not that the game plays on a cloud server. The game really plays peer-to-peer between all the local parties. The reason for that is latency. If you are walking towards someone and you're shooting them, that needs to happen in perceptibly the same time on both machines, which means you only have, 10, 20 milliseconds to actually get that message over there and basic synchronization. If you go the long way through a cloud system, you just can't get that done. That also explains why for most of those games, you need to have your firewall open, or at least UPnP enabled, or any of those things, because a lot of that happens through UDP. So it happens locally, but what that means, though, is that the game's owner has a problem with observing what's going on. And so they want to go and optimize the multiplayer maps. And so now what they're doing these days is they actually spool down telemetry from those games so that they learn what happens with the tank that they put on that multiplayer map. Who's picking up that tank? What is being done with that tank? So they learn about optimizing the game experience for you by instrumenting it. And of course, your entire career in Halo, if you are going up the ranks, that's all captured also in telemetry. Halo used event hubs in the first week, so Halo 5. We had 1.1 million events per second sustained out of the Halo game on the launch weekend, which is the busiest weekend for every game title. And then, of course, cloud operations is a big thing. Lots and lots of our traffic really comes from applications that are pushing events locally, locally in the data center into analytics pipelines. So we have, after this intro, we have a number of services. We have notification hubs, logic apps, service bus queues, Azure Queues 2, event hubs, Event Grid, IoT Hub, and the relay as services that are then combined with capabilities that we have in the cloud, directly integrated storage blobs, data lake, stream analytics, Storm Spark, Azure Functions, and all those things. Why so many? And they're doing a lot of work. 5.1 trillion events per week by now in event hubs. We run at a success rate of almost 5 nines, which is a big hill that we had to climb to get there. But there's also more work to be done, because if you think about what 5 nines, what that 99.9984% means at the rate of 5.1 trillion, is that we still have hundreds of millions of errors per week in the system, because those systems are very large. 28 petabytes of volume. And these numbers are growing very rapidly, which means we're rolling more and more capacity into all the data centers globally. So why so many different pigeons? Why do we have so many messaging systems? And that requires a bit of analysis and a bit of taxonomy thinking about what messages really are. Because it really depends on what you do. And when I just say depends, you're like, okay, what does it depend on? So I'm going to try to give you some guidance on that depends piece. Here are a few sets of messages, kinds of messages. And this is not an exhaustive list. We have commands, queries, jobs, updates, requests, notifications, assignments, reports, transfers, measurements, handovers, traces, as some candidates. I can go and group those. And that grouping is quite meaningful. I'll group them for you. Look at that for a moment. There's a key difference between the left side and the right side. The key difference is that this here, that left side, is all about me having expectations of something happening as I sent that message. Here, I'm basically saying what just happened. I'm talking about past facts. So I call that different intents versus facts. Intents are expectations, conversations, contracts, behavioral contracts that are being closed. I sent you this and you sent me that, maybe later. I transfer control to you, right? I'm an e-commerce website, and I do the catalog management and I collect your shopping cart. But once I have the order in hands and the customer said, yes, I want this, I'm going to hand that over to you for fulfillment. I'm done, but you need to go and carry that forward. I have the expectation that that handover happens and that now control flows. Or value transfer, right? As I talked about the financial services industry, in financial services, often messages literally represent money. And really also a purchase order that flows also represents money. If you fumble that purchase order is gone with that money. And the customer will be very unhappy. Facts are different. Facts represent history, things that you have already done. They have some context. They have some order in time, and they're schematized in some way, but they're just information. We'll create some further substructure around the facts in a moment. So that's how I split the world up. There's messaging, and there's eventing. Messaging is about fulfilling expectations, having conversations, talking to each other. Eventing is about reporting facts and acting and deriving insights from those facts, and then potentially even acting on those facts, but not based on expectation by the sender, which has architectural consequences, as you'll see in a moment. Messaging is about talking amongst each other. Eventing is about telling the world about something that happened. Events now fall into two different classes. There are discrete events. They are independent. They report state change. They are actionable, often. And then there are series events. They're time-ordered. They're context partitions. You go and put them into different partitions of a log so you can go and process them. They report a certain condition. And while they might not be immediately actionable, they're analyzable, and then you can go and derive some action from that analysis. Because those events are discrete, because they're singular, they're independent, that enables a different pattern of consumption because you can go and push them out. You can push them to someone rather than asking them to pull them like a series event. Why do you need to have a series? Why are series data such that you have to pull it? Well, what do you do with these series events? You go and analyze them. You do complex event processing. You want to have the average or a trend of a certain value over time. When you do a temperature reading in this room, where I'm getting a little toasty right now, but that's just me, and you want to go and control the air condition, you will not act on point observations because that might be quite dumb. So you have a temperature sensor that hangs right over here, and there will be temperature sensors in this room. And of course, this air in this room has certain dynamics, like it floats, and there's different zones of heat, etc., and where it's cool and whatnot. The temperature sensor exhibits significant jitter. It may go 2-3 degrees off in each direction, depending on what that sort of air is that just comes by. You don't want to go and act on that on a single reading. You want to act on the average or on a trend. What that means is, for that control logic, you need to pull that data towards you and compute an average over a time window. There's no place that information could be pushed to because nobody knows where that code lives that does that control for that particular heater. So it goes and pulls that stream towards it so it can go and keep that time window filled and then compute the average. And then based on the average, if that moves within a certain time window, it will then go and change the heat and basically turn the fan on or turn the cooling on. When the light turns off and it gets dark, well, that's a more discrete thing. And you may want to go and react to that by turning the emergency lights on. That's something that's more suited to push. Just for you to have a notion of analytics-based insights that cause action, and something that is a very discrete event that is more suitable to push to a stateless handler. So you will see here a model which is more suited to pulling through a messaging protocol, while you see here a case which is quite well suited to being to distribution through a push protocol like HTTP. And of course, that's also easier to scale out. So we're going to make this more concrete by looking at some scenarios here. So we have the sensor reading. As I just explained, you have a temperature reading, or you have a vibration reading. Vibration and temperature readings are in industrial manufacturing, in effectively most fields of industrial systems, the two most important metrics. You can solve a lot of problems in the world by just measuring their temperature and the vibration on practically everything. If it vibrates, and it vibrates a lot, it's broken. Michael laughs because he knows he's working on a lot of those systems. If something shakes a lot, there's a problem. That is really important. Like these sorts of observations are really, really critically important, like mission critical in many systems. Let me give you one more example of that kind of observation of vibration. There's a company, I listened to a talk that was 2 years ago, I think, but I found that example very compelling. A pharmaceutical company in Switzerland, and they have these clean room boxes, basically these glass boxes where you have to stick the gloves in, and that's the last stage of kind of finalizing the pharmaceutical product. And when they move a batch of that pharmaceutical product into that final stage, that batch is worth 250,000 euros, like in raw materials. It is ridiculously expensive. And if the airflow in that box is wrong, that is ruined, because the entire manufacturing process for that pharmaceutical needs to run under completely deterministic conditions. So they will need to know whether that box and all the fans in that box will work for the next 2 hours. Because otherwise it's wasted. And if they don't know, if they're not sure, they're going to go and change them, because changing those fans is cheap. But throwing that product away, that is not cheap. So again, that's all based on analytics. And that's all done by doing observations, pulling the data towards you, and figuring out what are the chances of those fans breaking. That means the analyzer is stateful. And it needs to do this fast, right? In most of those cases, because we're talking about, I gave you the numbers for a reason. There's 5.1 trillion events that we're pulling into the Event Hub's infrastructure per week. Many customers are pushing thousands of messages per second. There's no time for you to put things on the side, do it in a database. No, you have to do that in memory. If you do it in memory, there's one place where the master copy of that time window is, and there's one machine. You can't know where that is if you have a scaled out system, so that one machine needs to go and pull the data towards it. That's why you do pull on the sensor readings. This is done with having an ingester in the middle, and that ingester exists in two forms inside of Azure. We have an IoT hub. The IoT hub is built to attach devices directly or through a gateway, for which we also have a wonderful SDK. And that allows you to put telemetry into the cloud and then pull that out for processing. And Event Hubs is effectively the same thing as a generic capability that works for everything and isn't really scoped to devices. And then also, of course, if you want to go and run things in containers, you'll be familiar with Apache Kafka. If you want to run that yourself, you can do this. It's a little bit more complicated and not quite as reliable as using Event Hubs, but certainly if your application depends on that, you can go and use that. Discrete, so these were series events. Discrete events are a little different. you have an alarm from a device. The alarm is being raised. Here is something broken in that device. Devices may fire alarms for various reasons. But those alarms, like when the device really says, hey, I need to have attention, that is quite rare. And generally, these discrete events are fairly rare. So if you have some process that just sits there, spinning, waiting for 1 out of 20 devices to give you an alarm, and that alarm never happens, think of an alarm like, who has a smoke alarm in their house or in their rooms? We all need that now, yes. See, that's the kind of alarm. Do you want to run a process day and night to wait for that alarm to go off? I don't think so. I mean, someone needs to go and listen. So think of that kind of alarm. It never happens, hopefully. But when it happens, someone needs to be there. That's the kind of model that really is very well suited for this distribution. You route the alarm to a distributor. The distributor has subscriptions, and those subscriptions then get pushed to a handler, and that handler wakes up. It only gets activated ever if that alarm happens. If you pull, you need to pull and you need to be up as long as your analysis lasts, which might be forever. If you are reacting to a discrete event, you don't need to be up at all times. And this model is really well suited for serverless. IoT Hub Routes does that, and the Event Grid is the platform built-in capability that enables that. And I'm going to show you that in a second, how that actually looks. Messaging. This is now about communication, 2 ways. So I have a backend process. I have another device. I use devices here mostly because they illustrate the case pretty well. And I can talk about devices as things that you can picture. So let's say that device is your car. And the function we have here is a phone network connected key. And since phone network connected things are best hosted in your phone, that's an app. And so now you have an app that allows you to go and unlock your car. Everybody has that now. But how does that work? Because the car is far away. The car hangs on a cloud gateway that has a little queue through which it communicates. Why is there a queue? Because the car goes through tunnels, sits in garages, goes in and out of coverage. You know how that is if you drive far out in the country. And so there's these little queues which deal with all the network switching. And then there's a backend process. Now, your phone app will be talking to a mobile site, and that mobile site will talk to that backend. That backend will then talk to the car and will then feed back where your car is, whether the car is locked, and will allow you to go and send a command that will lock the car if it's not locked. That's a communication path, bidirectional communication. That's a messaging path to your car. And then, of course, back-end processing, heavy lifting. That's what we all do. I talked about banking. I talked about energy. I talked about all those cases. There's typically some processes that are happening based on a job. You process that job using a workflow. You hand off the result to some accounting thing that goes and turns that into money in some way. That's a classic case for messaging. Oh, I didn't talk about the previous example. So the example here, on that example, IoT Hub does cloud to device communication. The generic case for that is Service Bus. That allows to send to everybody, not just to devices. And then workflow execution, logic apps, and Service Bus are the 2 platforms for that style of messaging. And then we have this hybrid cloud scenario. And hybrid cloud is kind of funny because everybody has it in some way who's building sophisticated business systems. You have a branch office, and that branch office or the work site needs to work independent of anything you put into the cloud. If you run a chain of pizza stores, pizza restaurants. If you can't bake pizzas, if your internet connection is down, something is wrong, that is enormously stupid. And you'll all recognize that as being stupid. Imagine you walk into a pizza store and say, I would like to have this pizza. And they say, I can't do that because the cloud is down. Unacceptable. Unacceptable in many, many scenarios. Let's talk about something that's more serious. A factory. You have a factory environment. You have robots putting stuff together. And suddenly the whole line stops because the internet connection is down. Unacceptable. Also because as that line goes down, it might kill people. So, unacceptable. Your car drives towards an obstacle, and it can't see it because the internet connection doesn't work, and the analytics would be run in the cloud. Unacceptable, right? So there's a lot of stuff that needs to happen locally. But you need to have that integration. You want to be able, from a back-end process, to go and send data. Let's go back to the pizza place. You have a web portal that accepts your pizza order. You want to be able to dispatch that into the pizza store. How do you do that? Well, using a message. Or using the relay. What the relay allows you to do is to put a network listener. You can put a database on premises, or still have it on premises, and connect to it through firewalls and through NATs, as if they were part of the cloud system, because we can go and build a bridge to that without VPN, without having to punch any holes into the firewall inbound, but the relay actually magically does that for you. So that's for that scenario. And then, of course, for devices and web, notifications, status, feedback, commands into a phone or an IoT device or a browser. If you want to have status of what's going on in your backend process, we have notification hubs, we have IoT hub, we have service bus, we have Signal R, which you can put on top of this, all infrastructure that can go and help with that case. So you'll see how there's different cases and different appropriate infrastructure to apply to those cases. And that's why we have so many. The thing I really want to show you, because it's new and you may not be familiar with it, is Event Hubs, Event Grid. And we built Event Grid specifically for the case of discrete events. Because discrete events are something that's relatively new and novel as an architectural pattern in conjunction with the serverless trend. What they allow is extensibility. So what I said in the beginning was event grids, discrete events are independent. They don't depend on anything. And they typically represent state changes, and they're actionable. That means you can now tell the world about stuff that happened, and the world can go and react to that stuff that happened and then use that as an extensibility hook. And I'll show you an example about that. With the event grid, we can now allow you to extend the storage service. So here's my portal. We have here a storage account. So interestingly enough, look at me. I'm a messenger. I'm showing you a storage account. That's a little weird. What we did in Azure now with the event grid is we pulled an event plane underneath the entire platform. So you don't create an event grid. The event grid exists. It exists underneath Azure. We currently have that in preview. We're going to have that in all data centers as an extensibility fabric that sits underneath the system. And now you can go and make your storage account. You can extend the functionality of your storage account with magic. So I have here a storage account, and you'll notice that there's a new thing called the event grid. And if you go into the documentation, there's a few things you need to do to go and activate this. So you need to go enable this feature, but once you've enabled that feature, you will see the event grid. And you can go and create event subscriptions, and I already made one. So here's that event subscription. What does that do? So I have a name, And now I have an event type that I can go and select, and I can go and act on blob created and blob deleted. I select all of them here. I have an endpoint that I give, and that's a webhook that I can go and send to. And then I can go and filter out a suffix. Right? The create experience looks almost like this, so let's go and look at that. So you give a name. You automatically subscribe to all event types. If you don't, you have the ability to go and subscribe to selected ones. And we currently only have webhook, but we will have native integration, direct integration with Azure Functions and with logic apps and some other syncs, so you don't have to go and type in a URI. But right now, that's what the status is. All right, so if I then go, so what, oops, oh, that would be dumb, okay. Oh no, I have to do that, sorry. Yes, okay. So, now, what does that do? When a blob gets created in that container, I will now raise an event. I'm not going to do this because the setting up of the Cloud Shell takes a little while, and I don't want to do that to you. But if you are now creating a file, so if I upload a file into the container, I'm going to get an event that looks like this. I did this with request bin, as you see. So the motion here is simply I upload a file and then I get this request. And here's what I see. I filtered on .txt, so that's why I get this event. So I now created a new block blob, and that's the information that I get. And I get, what's the content of that file, and some information about it, like when it was, what the operation was, etc. So now so this is very simple. Think of the possibilities. Let's say you're building a photo library. You can now make your storage account a photo library. You're waiting for the blob created event on a JPEG. You're being called. You're reading the file. You create 5 thumbnail files and put them into the thumbnail folder. Automatic. You don't need to pull. You don't need to do anything. That function gets called whenever something gets uploaded. You can do effectively post-processing of uploaded files completely automatically by a trigger. Put that in the context of an application that you built yourself. Let's say you have an application that captures sales leads for a sales support application. And you fire the event called sales lead created. You do nothing but you just fire that event. You don't think about anybody who consumes it. Then you're running an internal house trade show in 4 weeks. You already sent the mailing out to everybody, all of your existing accounts, and now you want to notify every new sales lead who comes in after you send out that mailing. You want to send them in an extra mail. How do you do that? You just hook up to that event. And you write that little function that goes and gets the data and sends that email. That's all. And then once that event is done, you toss that function out. You created an extension to a core business application without the business application even knowing about it. Because you're firing events out. You're distributing facts that you created inside of your application and use those as extension hooks. That's what the power of the event grid is. It allows you to extend functionality into your application. What we have in terms of support here is events fired from blob storage, from resource groups. So Azure Resource Manager, we can now tell you when a VM has been deployed. We can tell you when all the resources are being deployed. You can go and react them to continue your workflow based on that. You can know when an event hub is done dropping a file into the data lake or into storage. You can know about things that IoT Hub does. That's going to be disclosed later. And of course, you can build your own topics for your own applications. And they're going to have automatic implement hooks into webhooks. You've seen that already. And we're going to have Azure Functions, Logic Apps, Azure Automation, all automatically hooked up. And the nice thing is you don't need to go and create this. It's just an built-in capability to go and capture events that happen in Azure and then move them and erase them into other applications. As said, this shows up as a feature of blob storage. It shows up as a feature of all those different services. It's not something you create that sits in the middle, but it becomes a native feature of the Azure platform per se, to allow, and becomes a feature of your application as well. So you don't need to go and create a thing. The thing already exists because we're building that into the foundation of the Azure platform as an event plane. The scale of this is we're initially going for a capacity of 10 million events per second per Azure region. And we know how to scale that up pretty well because there's really no limits, but that's the capacity that we're starting with. 10 million events per second is pretty fast. And so that's the initial capacity that we plan for all the regions. So I hope that was somewhat enlightening. We have a lot of options for many different scenarios. I went through scenarios for Event Hubs, for IoT Hub, for Event Grid, for Service Bus, also for Logic Apps, Notification Hubs. Like, I covered all of them. And you'll be able to also find that deck for reference, via my Twitter, and obviously also through the conference website eventually when that is made available. As said, I hope that was useful. Thank you very much for listening to me today, and have a good rest of your conference.